In this video, we're going to look at confidence intervals for population proportions. So we know that we use sample proportions to estimate what the population proportion is. But when we do that, we want to know how accurate is it? And so we need some way of measuring the level of accuracy of our estimate. Is it a good estimate? Is it a very good estimate? Is it an excellent estimate? We'll also explore the idea of the sample proportion being what we call a point estimate of the population proportion. We'll also look at the idea of, rather than just taking a single value as an estimate, what if we add a little bit of a margin of error on either side to our estimate, so that we have a better estimate of the population proportion. And then moving on to recognizing that actually the best estimate is actually going to be an interval, which we hope will contain P. And we can talk about how confident we are that that sort of interval, the interval that we choose to use, the size of the interval that we choose to use, how confident with that we are that it actually contains the population proportion in between our lower value for the interval and our upper value for the interval. So let's start with this idea of a point estimate. So here I have some data that I collected from a large population. I took 13 samples from a large population, and I calculated the sample proportion for each one. So sample 1 had a sample proportion of 0.42. And this is its sample proportion. So it's sample 1, so it's going to sit over here. Population, sample proportion of 0.42, so it sits here. I then generated another sample. Its population proportion was 0.48, and you can see 0.75, 0.61, 0.38, and you can see each sample is generating a different value for the sample proportion, and that's what you would expect because the sample proportion is a random variable. The aim of all these sample proportions is to estimate what the population proportion is. So we have to somehow or other find some way of linking all of these values together to find a population proportion. So we're going to do it in a very rough manner. We're going to do it trying to use a straight line to fit here. So here is a line that we're going to try and fit to as many of those dots as possible. So for anybody that's doing further maths, you'll recognise this as a line of best fit. We could use the residuals to try and find the best one, and possibly we could figure out that maybe our sample proportion fits in here somewhere. So that's one way of doing an estimate, but how good of an estimate is that? So maybe what we could do is add a little bit of an error on either side. So for our work with probability earlier, we know for a distribution that if you take the mean and move down 2 standard deviations, so you're creating a little bit of there's your mean, we come down 2 standard deviations, that between here and 2 standard deviations up above, between here, that for that interval there, approximately 95% of the values sit in there. So let's try using this idea of an interval to help us to get a better estimate of where this line should be. So here I've added a margin of error to each of the estimates, and the margin of error is the little green line on either side. So I now have an interval, so the red is still the sample proportion, and to each of the values up here I've set my margin of error at 0.05. So from our sample proportion, we add 0.05 to get 0.47, which is this value at the top, and then from 0.42 we minus 0.05 to get 0.375, and I've done that to each of the samples and created this little interval for each of our samples. And you can see that you can start to get a better feel for where the actual line of best fit should possibly go, up or down here. Judge it, and we're judging it by how many of these particular intervals this line of best fit, if you like, actually fits through. Remember, this is the actual meant to be the population proportion as well. So we could count how many of these little intervals it passes through to give us an indication of how accurate our measurement is. So the size of the margin of error is up to us. So let's try increasing this margin of error a little bit and see what happens with where our line is sitting. So I've doubled our margin of error, and so our little intervals are becoming wider. And if we take our line for our estimate of our population proportion, you can see that as we move the line up and down, we're being contained within more of those intervals. Now, the underlying population proportion for this population, because obviously I've set these values up here with an underlying distribution, and I can tell you that the underlying population has a population proportion of 0.6. And so now we can start to think about how well do our samples with our intervals, how many of them are actually containing that population proportion. So here we've got 1, 2, 3, 4, 5, 6 of our samples. Half of our samples are containing, roughly half of our samples are actually containing the population proportion. If we made the margin of error bigger, what will happen? So I've doubled the margin of error again, and I'll just fill in the intervals for us so we can see them very clearly. And now you can see that there's only a couple of intervals, this one here and this one here, that don't contain the population proportion. And so now we've got 11 out of 13 of our samples with their intervals attached containing the population proportion. And so we've now got a measure of how confident we can be that a sample that we make with this particular margin of error is actually going to be containing the population proportion. And this is where our level of confidence for our confidence interval comes from. What proportion of our samples is actually going to contain that population proportion? So now we're going to talk about how we figure out what our margin of error should be so that we can work out how confident we should be that the intervals that we're using are going to contain the population proportion. So let's have a look at that. So let's look at the margin of error and this idea of a confidence interval. So each of our samples had a red dot for its p-hat value, and these green sections represented our margin of error. And so what we've got here is an interval with an upper value of whatever this is and a lower value of whatever this is. So let's use one of our samples so that we can make sense of exactly where these values come from. So let's use sample 1, and for sample 1 p hat was 0.42. So this value here is 0.42. Let's go with a margin of error of 0.2, which means that this distance here is 0.2. So we need to come down, so this distance here is 0.2. So that makes our lower value here 0.22. We do the same at the top end, put our margin of error on, so that's 0.2, which makes our top value 0.62. And so these two yellow values are the values that we put into our confidence interval. So our confidence interval for this particular sample goes from 0.22 to 0.62. So it looks like it looks like the coordinates of a point, but this is actually a confidence interval, and you can think of it as being an open-ended interval that goes from 0.22 to 0.62. If you think of that as a number line, it would be an interval. So for sample number 1, our confidence interval, CI, is from 0.22 to 0.62. And when we used a margin of error of 0.2 of our 13 samples that we had, 11 out of the 13, or approximately 85% of our samples, contained the population proportion, and so we can be 85% certain that this confidence interval here is going to contain the actual population proportion. Sample 2 will also have its own confidence interval. Let's look at that. So for sample 2, our sample proportion was 0.48, and the margin of error that we're using is 0.2. If we add 0.2, we're going to get the upper value for our confidence interval, and if we subtract 0.2, we're going to get our lower value for our confidence interval. And because we're using the same margin of error as we used over here, this confidence interval, we can also be 85% sure that of all the samples using that particular margin of error, that the population proportion will be in 85% of those samples. If we change the margin of error, that changes the width of these bars, and of course, if you remember back to when we were changing these sizes, the smaller the margin of error, the less likely it is for the population proportion to sit between the lower and the upper value. But let's look at how we actually determine what margin of error to use. So our margin of error is in fact a multiple of the estimated value of the population standard deviation. So we know for a very large population that a characteristic or an attribute, something that we're looking for, is distributed normally with a mean equal to the population proportion and the standard deviation for that normal distribution equal to this, where n is our sample size that we're using to sample with. And so our margin of error is a multiple of this. And in the textbook, they use a k to represent that multiple. And so what we've got for our confidence intervals that we're creating is that we are using our p hat minus our margin of error. So our margin of error, remember, is k times an estimate, and we're using our p hat value here to estimate theta. And so our confidence interval is going from p hat minus some multiple of that standard deviation, and that has been our confidence interval. And I want you to have a look at the relationship between what I've got here and what we've got here. We know that our mean is our population proportion, but the only thing we've got to estimate our population proportion is a p hat. So we could put a p hat here, and we could turn our standard deviation into a green one, and we've got a k value of 3 here and a k value of 3 here. And we know from our previous work that if you start with the mean and you go 3 standard deviations either side of the mean to get 2 values, approximately 0.997% of your values will lie in there. If we go out 2 standard deviations below, 2 standard deviations above, we get approximately 0.95%. However, for our confidence interval, the percentage that sat off here to the side, whatever our percentage was, something percent, wasn't the probability that the value was lying between these two, but was actually an indication of how many, or more precisely, what proportion of these sorts of samples would contain the population proportion. And so we can simplify this all together. Simplify, it's going to look a little bit worse than simplify, but we can pull all of this together to come up with this statement down here. If we have the sample proportion and we take away some multiple of the standard deviation, the estimated standard deviation, and we have the sample proportion and we add some multiple of the estimated population standard deviation, we've got some percentage that we can use to talk about how confident we are that we've actually captured that population proportion. Now, I want to talk about how we work out this k value next. So you'll notice that where I've got up here, where I've got it's between 3 standard deviations to the left and the right, and I've got that it's approximately this value. Hopefully your work with normal distribution has allowed you to see that actually there is a specific value that goes here, and it's not 3 that gives you 0.997, and there's a specific value that goes here, and it's not 2 that gives you 0.95. Let's look at how we determine what that k value is. To determine the values of k, we use our standard normal distribution that has a mean of 0 and a standard deviation of 1. If we want to know exactly the values of k that contain that 0.95 area, what we do is we put a middle area on our distribution to k, and we contain 0.95 of that area, 95% of that area, between those two K values. To work this out, we're going to use inverse normal on our CAS calculator, and remember, inverse normal works for the TI on the area that you put in is always read from negative infinity. So we're going to, on our CAS calculator, we're going to put in this area here, which is going to be half of what's left over from the 0.95 difference to 1. So the total area's got to be 1. So we've got 0.95. So we've got 0.05 made up of this bit and this bit, which means this area here is 0.025. And when we put that value into our inverse normal with our standard normal with a mean of 0, standard deviation of 1, we get minus 1.96. So our K value here is minus 1.96. So negative 1.96 on this end and 1.96 on the other end. If we wanted to do the same thing for a confidence interval level of not 95% but 90%, we would set up our standard deviation diagram with 90% in the middle, so minus K at the lower end, K at the upper end. So we've got 90% in the middle, which means the two end areas here and here make up 10%. So this area is going to be 0.05. We'll do our inverse normal on our CAS calculator with that, and this time when we do that, here we'll put 0.05. This time when you do that, you get a K value of 1.6, and we'll round this to 1.65. And so our K value is 1.65. So now we can use these K values to write formulae for our confidence intervals. So for our 95% confidence interval, our lower value for our confidence interval is our P hat minus 1.96, our K value for 95. So our 95% interval in our Z distribution, our K value is 1.96, so that's what goes there, multiplied by our estimate of our standard deviation. So that's our lower one, where you subtract that, and our upper one is exactly this, with this changed to a plus. For our, let's just squeeze this in so we can see, for our 90% confidence interval, we will get exactly the same setup as the one above. The only difference will be where the 95% has 1.96. Our K value to go in here will be the K value for 90% in the middle for the standard deviation. So our K value for both of these is going to be 1.65. And that's how you work out your confidence intervals for whatever confidence interval you want, whatever percentage you want. The K value is determined by the percentage that you want to have the sample proportion contained within them. So using this formula here to generate a confidence interval from a sample that we've taken, we can be confident that 90% of any samples that we take using this particular formula, 90% of those samples will contain, between the lower value and the higher value, will contain the actual population proportion.